Okay, so we're very happy to have Luigi Tizzano, who will tell us about anomaly matching across dimensions and supersymmetric Cardy formula.
Okay. Thank you so much for having me, for giving me the opportunity to speak here. And so the goal of my talk today will be to study certain aspects of the theory of anomalies and to apply them to the problem of quantum field theories of finite temperature in such a way that we will be able to study certain high temperature limits of partition function in 4 dimensions, and to apply this problem to both cases where you have and you don't have supersymmetry. So let me remind you a bit about certain basic aspects of thermal field theory. So in this talk, I will consider mostly a theory in 4 dimensions with a global U1 symmetry, and I want to place that at finite temperature T. So it is usually standard in order to study such the finite temperature effects to place the theory on a compact manifold, which is the product of M3 times S1. And I'm going to take the radius of the circle beta to be and identify that with the inverse temperature. And so the traditional idea is that below the Kaluza-Klein scale, that is 1 over beta, you expect that the theory, like that the theory has a thermal gap, and you can describe the theory on M3 on the 3 manifold by a local theory. And in general, to compute the correlation function in this theory, you will have to work out the thermal effective action, which is going to depend on 2 data mostly, which are the background field capital A here, and on the metric. And so in particular, the metric that we're going to choose for the thermal background has a non-trivial Kaluza-Klein photon. So we should not think about this metric as a direct product, but as a fibered metric. And this will be important in many applications that I'm going to discuss today. Okay, so then this effective functional admits a derivative expansion, and then one can sit down and try to classify all the terms that are available and could enter such derivative expansion. But luckily, at first ordering derivatives, such terms in 4 dimensions have been classified, and we know that there is an effective functional that takes the following form. And this effective functional has 2 types of contribution. There is this contribution that multiplies a coefficient C, and then there is this other contribution that multiplies a coefficient K1. And I will often refer to this kind of terms as Chern-Simons contact terms. Okay, anyway, the term with coefficient C, as you can notice, it's associated with these Chern-Simons terms, but it's kind of problematic because this A of tau here is a general function on the base manifold. And so all these terms are not invariant under small gauge transformation. So a priori, this term looks problematic in the effective action. However, there is an interesting twist in this story that comes from considering the fact that the 4-dimensional theory that we begin with on M3 times S1 could have a Hooft anomaly for the U1 global symmetry. And in fact, it was shown in this very nice sequence of paper that you can match the anomalous variation of this term in the 3D effective action using the Hooft anomaly, the cubic Hooft anomaly for this U1 symmetry in 4 dimensions. And so this circle of ideas that correlate anomalies in theories at finite temperature is sometimes called an anomaly matching across dimensions. So you imagine that certain anomalous variation of an effective action could be matched by a parent theory in 1 higher dimension. However, as you can notice, the other term, the one that multiplies K1, is more subtle because this term, as you can see here, is perfectly fine under small gauge transformation. And so you wouldn't imagine that anomalies have anything to do with this term. But already quite some time ago, it was discovered in a series of holographic computation that surprisingly, the value of K1 is fixed to be exactly this -1 over 12 times KU1, where KU1 is the coefficient of an anomaly between U1 and gravity. So it's a Hooft anomaly, so a mixed Hooft anomaly between U1 and the gravitational background. And so there has been a lot of study in order to understand why you have to fix the term in the effective action in this way. So the main proposal are two. So if the theory that we are beginning with can be described by a Lagrangian description, so it's some weakly coupled theory that you put at finite temperature, then you can fix the value of K1 to be exactly this value using a very nice non-renormalization argument. And this was shown some time ago in this work by Di Pietro and Komargodski. However, if you happen to be interested in a theory that is at strong coupling, you cannot really use this non-renormalization argument because you cannot go to a point in modulus, you cannot go to a point where the theory is free, and so you cannot really compute this coefficient in a free theory. And so it was proposed very interestingly some time ago by these authors that maybe in order to fix this coefficient, you have to place the theory on some conical geometry. And the reason for the conical geometry is because it appears somewhat strange that the gravitational anomaly, which enters at higher order in derivative usually, would contribute at first order in derivative. So these authors imagine that if you try to study the theory on a singular background, you could have such a mismatch in the derivative expansion. However, studying a theory in a conical geometry is very subtle. And so because there could be localized states and stuff that we don't fully understand. And so it would be nice and interesting to find a slightly different reformulation of this problem. And this is what we decided to tackle in my paper with Cantaro. So let me remind you some facts about anomalies and then how we apply them in the finite temperature situation. So recall that the anomaly polynomial for a theory with a U1 global symmetry is this sixth form, where C1 and P1 are two characteristic classes which are built out of the background field for the U1 symmetry B. So this is C1 would be just its field strength. And P1 is the trace of the Riemann, P1 is expressed in terms of the trace of the Riemann curvature tensor. So associated to this sixth form, we can then define a Chern-Simons functional in this way. And this Chern-Simons functional is obtained by considering a manifold Y6, which is a bulk extension of the manifold N5, where the Chern-Simons is defined. And we have to make sure that we have to perform certain choices of the extension Y6 to make sure that this functional is a well-defined Chern-Simons functional in 5 dimensions. So let me add a word on notation. In what follows, I will always denote the background field with a hat to be the background field on the 5 manifold, and the background field with a tilde to be the extension of the background on the 6 manifold. Okay. So you probably have heard that recently people like to call this kind of Chern-Simons functional as invertible field theory. But really, we don't really need right now the theory of this object, but just, remember this as a name. And anyway, what we are going to do now is to further assume that this 5 manifold has the topology of some other 4 manifolds times a circle. And then to study the reduction of this Chern-Simons functional on a circle to find some other 4-dimensional invertible theory that we want to determine. And that will be important to match the anomalous variation of the functional that we are after. But in order to do that, we have to discuss a bit more the topology of the manifold, of the 6 manifold. So imagine that we pick the 6 manifold to be, so what we are going to do is to pick this 6 manifold to be the product of N4 times the disk, where we equip the disk with a cigar metric in this way. So basically, we take this 4 manifold and we attach the disk in this way. And we ask, so here R is the radial coordinate on the disk, and we place the boundary at 1. And then we require that this function G of R is 0 at the tip of the disk, of the cigar, so that this metric is moved there. And then in this background, we will denote the field strength that of the U1 symmetry by F tilde, as I told you before. So when you have this background, you have to we define what we call the thermal anomaly polynomial, which is, we want to calculate the 6-form anomaly polynomial in this specific background. And that depends on this choice of extension and on the extension of the field strength for the U1 symmetry. So now, once we have this data, we can reduce to a 4-dimensional invertible theory by integrating over this disk. And in order to do that, so we literally have to compute the reduction of this integral over the disk. But there is an important point that we need to remember, is that because we choose a metric that is the metric of a cigar, the contribution from this first characteristic class splits in the contribution of 2 pieces. The first Pontryagin of the four manifold, and then there is a non-vanishing contribution from the tangent bundle of this disk, which you can also relate to the Euler class of the disk. And this contribution is extremely important to understand what people have associated to the jumping derivative of the effective action. So it's due to the fact that you have this fiber background when you consider the anomaly in this 6-dimensional space. So then if we reduce this 6D 6 form on the disk using the prescription that I gave you for the metric and for this F tilde, we will find a functional, which is a four form functional, which is made of these following background fields. And the A hat tau field here should be thought of as a periodic scalar background, which is basically the scalar background that is periodic because there is a non-trivial circle where we are reducing this function. So you could, in fact, model this you can think about this as some kind of periodic axiom. And in fact, the study of this kind of invertible theory with a periodic scalar have been kind of very studied recently, starting with this work here. Okay, so then the last step is to find the anomalous variation that we were after. And in order to do that, we have to assume that the N4 can also have a boundary, or more precisely, we assume that N4 is the bulk extension to the 3 manifold that we begin with. So then if we fix the A at tau, so we fix the axiom to be as so we integrate it to a constant along N4. So we treat it as a chemical potential for the thermal isometry. We can finally integrate this QT over the 4 manifold and obtain precisely this contribution from the anomaly. And if you compare with the formula that I write at the beginning, it's very easy to see that we can fix both the coefficient C from the cubic anomaly, and we can also fix the coefficient K1 in a way that only depends on the anomaly and does not depend on the computation of the theory of weak coupling. So this is, a new derivation of this formula that does not rely on the previous assumption that were given in the literature. Okay, so far, everything I told you is about non-supersymmetric theories, but then this can also be applied to study certain problems with supersymmetry. And one particular problem where this becomes extremely interesting is the context of a superconformal field theory in 4 dimensions, where one often wants to study the partition function on S3 times S1 with a periodic boundary condition for the fermions, which is also known as the superconformal index. This is a very important observable because it counts supersymmetric states on S3 times R, and we correlate this counting to the counting of BPS local operator in flat space. And it is also known that this observable is very special because it's completely independent of exactly marginal deformation. And we can define it as the trace over the Hilbert space of the theory on S3, with refined by 2 fugacities for the angular momenta J1 and J2. These are the angular momenta of SU2 times SU2. And we denote by R the U1R charge that is always available for n=1 SCFTs. For theories with a Lagrangian description, this index can also be computed by placing the theory in a supersymmetric S3 times S1 background, and then performing the localization computation. And in the end, the result that you get is a unitary matrix integral that can be analyzed in various regimes. However, an important point is that the partition function on S3 times S1 is actually a geometrization of the superconformal index. in a sense that we can identify these fugacities omega 1 and omega 2 with certain complex structure moduli that we have if we think about this manifold as a complex manifold and then as a particular example in the family of the Hooft surfaces. So this point of view is very useful because it makes us think about the index directly as a holomorphic function of this parameter. And using this point of view, we can again prove certain renormalization theorems in a very convenient way. However, there is an important point is that the index as a function of this fugacity that can take complex value, it is not single valued. So you should really think about the index as something that lives on the cover of the moduli space of complex structure deformations. And so if we make periodic shifts of these fugacities and omega 1 and omega 2, the index can be shifted in a non-trivial way. And in particular, for n equal 1 SCFTs, we know that the index has two different sheets of validity. The first one is when n and 0 is 0, so we have the ordinary index. And the second one gives you a non-trivial result. So shifting omega by a multiple of 2 pi will land you on a different object, which I'm now going to define. But what does this mean geometrically? That means the following, that the SUSY background that we are studying on this S3 times S1 background has have fugacities identified with the following data, which are B, the squashing parameter for the metric on S3, and sigma 1 and sigma 2, which are twisting of the trisphere around S1. So you can see that by the shift that I gave here can be performed by shifting non-trivially these twisting parameters. So this tells you that if you want to probe the index on the first sheet where there is a non-trivial, on the second sheet when there is a non-trivial shift of the fugacities, you have to consider non-trivial twisting of the S3 over S1. And so again, it is very important to understand that this will not be, again, a direct product. So in this context, there is no really temperature because we are studying a supersymmetric theory, but there is a very interesting limit that we can perform, which is the Cardy limit, where we want to send both fugacities to 0 while keeping their ratio fixed. And if omega and 1 and omega 2 are real, this is really reminiscent of the ordinary Cardy limit where we send when we shrink the thermal circle to 0 in conformal field theories. However, because of what I said before, this is not the only way to take the Cardy limit. In fact, we can allow for complex value of the fugacities, then shift one of them, and only after study the Cardy limit. However, if we do this shift, because the index is not periodic in the fugacity omega 1, we will replace the index by this new object, which instead of having a periodicity set by -1 to the f, instead of having this -1 to the f here, has -1 to the f replaced by this -1 to the r charge. So this is still a BPS object, which is subject to the same BPS states, but it will be subject to a different pattern of cancellations of BPS states. And this property, this simple shift, had very, very important consequences for the study of ADS5 BPS black hole. And I hope to make some comment about it soon. Okay, so the problem is the following. If we want to study this beta to 0 limit or the supersymmetric Cardy limit, we can again try to introduce the same effective functional that we wrote down before, but then we have to write down a supersymmetric version of that functional. And this was studied in this nice paper. And in particular, the problem in the supersymmetric world is more constrained because everything that enters in this functional can be evaluated directly in terms of the supersymmetric curve background on S3 that we obtain from the theory when we reduce on the circle. And in particular, the metric and all the background fields have a profile that is completely fixed by the coupling to the background supergravity multiplet. So this is the standard story when we want to couple a theory to a curve background while preserving supersymmetry. And in particular, on the first sheet where we don't perform any shift of the fugacity, we know that the superconformal index has this Cardy limit. where Kr is the Hooft anomaly coefficient for the U1R symmetry now, which, as I said, is always present for this superconformal field theory. However, we can also probe the second sheet where we turn on this non-trivial value of n0. And then we will discover that the Cardy limit has a completely different behavior given by this formula. In particular, in this new regime, we can completely nail down all the terms that contribute to the Cardy limit up to exponentially small correction in beta. And this formula has been derived by various methods and has been tested in many ways, and it's a pretty striking formula. In particular, we know of a effective field theory derivation by the same logic that I told you before, but it can also be motivated by the analysis of the unitary matrix integral that we have when we perform the localization computation. And also we know of earlier computation of the same limit where this most singular term was already found out. So the prediction that come from the Cardy limit in this regime seem to be very robust. And because we see that the Hooft anomaly coefficients enter here and here, you could again wonder if the problem and the method that I explained before could be applied also to this problem. And this is exactly what we explored. Again, you know, we're going to have a superconformal field theory, which have in general a 6-form polynomial of this kind. And as before, the important point is that the metric on this spacetime is non-trivially fibered. And so we have to, if we want to discuss something like the thermal anomaly polynomial, as I told you before, we'll have to introduce this fibered 6 manifold and then define the extension of the background fields and of the metric on this, and which allows us to define the thermal anomaly polynomial. And then the proposal that we make in our paper is that we can obtain the Cardy limit on the second sheet by integrating again the thermal anomaly polynomial on this kind of spacetime. And again, here, the problem is even more constrained because the choice of metric and the choice of extension are dictated by the supersymmetric background that the theory has to be placed on when we want to study the superconformal field theory. So one could go about and try to perform this integral exactly in a similar way as I told you before. But it turns out that, there is a trick that we can use, which is very convenient in the study of supersymmetric theory. There is, we can use something called the equivariant integration. So if you have a smooth 2 even dimensional manifold, which admits a toric action, you can always define on this theory a new cohomology theory, that is the equivariant cohomology. And if this manifold has a discrete set of isolated fixed points, you can then prove a very important equivariant localization formula. That is, you can compute the integral of this form on the even dimensional manifold by summing over the discrete set of fixed points and evaluating the characteristic classes alpha and the Euler class of the tangent of the manifold, evaluate the restriction at the fixed point. And these fixed points are the fixed point under this toric action. And the basic idea is that you can think there is a very convenient way to do this kind of integration involving the anomaly polynomial. If we promote the anomaly polynomial to be an equivariant differential form, and we integrate it equivariantly according to this method. So this type of trick replaces the analysis that I made before in the non-supersymmetric case. Okay, so the catch is that we can then replace the choice of n4 times d2 by a 6 manifold, which is the product of r4 times r2, twisted by this equivariant parameter. And here I really use the value omega1 and omega2, meaning that I'm identifying the equivariant parameters on this space with the fugacities that enter in the definition of the superconformal index. And then what we have to do is to compute the equivariant integration of the anomaly polynomial on this 6 manifold. which according to the formula will be evaluated only on a single fixed point, because this is the unique fixed point on this M6. And this boils down in evaluating this formula here, where we just replace the expression for the anomaly polynomial that we found before, extended to this 6 manifold. Okay, there are various things that you have to determine in order to compute these characteristic classes, and we determine that in our paper, and they are based on the precise details of the supersymmetric background where the theory is placed on. And so if we put all together, we can evaluate the formula and find precisely all the terms that enter in the Cardy formula, except for the exponentially suppressed term. And so we can establish that the Cardy formula can be derived on this second sheet without relying on the Lagrangian description of the SCFT, because all we need to do in this formulation is to know the contribution from anomaly that is universal for this kind of superconformal field theories. As I wrote down before, there was also a contribution from the log of the order of G. And this contribution is interpreted in this business as coming from the effect of a spontaneously broken one-form symmetry whenever it is present. And so in order to capture this finite contribution, we would have to understand how to treat anomalies that involves this symmetry. And so this is something interesting to consider, but I don't have time to talk about it in more detail than this. And then a final exploration that we propose is that we can analyze this formula. So everything that goes inside this formula is basically the knowledge of anomalies and of the supersymmetric background of the theory. And so by similar methods, we can also explore a similar Cardy limit in 6-dimensional SCFTs, because that's all we need to know. And so we have some preliminary formula that we wrote down in our paper, and maybe a parallel analysis that would be interesting to do is to understand if there is a way to understand at least some of the contribution in this limit by studying some kind of effective field theory, maybe that would match some of these contributions. So, okay. Anyway, I want to thank you now because I ran over time, and I'm going to leave these slides as outlook. Okay. Thank you so much.
Thank you, Luigi, for the nice talk. Any questions for him?
Yeah, can I ask a question about this?
Yeah.
Hey, Luigi. So I was wondering about the spontaneously broken one-form symmetry that you mentioned. How should I be thinking about this?
So like
in an example,
just take n equal 4. N equal 4 is a theory, you know, that has a one-form symmetry, and at high temperature, the one-form symmetry is spontaneously broken. So this G would be Zn, G1 would be Zn, and the log of the order of G would be n.
Right.
So
but how should I be? What's the reason this is broken at high temperature? I've never. I don't know anything about this.
So well, it's not broken only at high. So n equal 4. So okay, a theory that preserves the one. So n equal 4 has a one-form symmetry because all the fields that compose the n equal 4 Lagrangian transform in the adjoint representation. But the theory clearly does not preserve the one-form symmetry, because preserving the one-form symmetry means that the theory confines. But n equal 4 doesn't confine. So the symmetry is always spontaneously broken. And at high temperature, it was proven by Witten a long time ago that that symmetry, in fact, is also spontaneously broken.
Okay. And for the 60 case, so is it trivial in this case to say consider like a Riemann surface compactification to 4D and somehow match the two descriptions?
That's more well, I'm not so sure, because the formula that we get in 6 dimension is the formula for, you know, the log, so the Cardy limit of the index in 6 dimension. And that is, you know, from that formula to the 4D formula, there is no well, from the point of view I'm treating it, I don't know of like a immediate relationship between. So in a sense, there are a lot of choices that depend on the Riemann surface and on the background that you turn on.
Right.
And one would have to think about this problem. I can't immediately say anything very concrete.
Okay. Thanks.
Any other questions? So I know you ran out of time, but can you say something quick about ADS5 BPS black hole?
Sure. Just I can flash these slides just for your interest. So this kind of motivates why we got all interested in this business. So as I told you before, on the first sheet, the asymptotic of the Cardy limit goes like KR, which is the UNR anomaly, Hooft anomaly coefficient. But on the second sheet, the most singular term is the difference of K cubic minus KR. So if you take n equal 4, it is known that KR is 0, but K cubic is not 0. So if you were using the prediction from the Cardy formula on the first sheet and then take the large n limit, you would see that this contribution could never match the entropy of a large BPS black hole because it gives you an order 1 contribution to the entropy. And in fact, this caused, this is a Cardy version of the entropy puzzle that has been around for many, many years in the study of BPS black hole. But the catch is that if we allow for a study, basically the index at these generic values of the fugacities, then we can take the Cardy limit here and only after take the large n limit and precisely match the Bekenstein-Hawking entropy of this BPS black hole. And when I say match, we match precisely the entire contribution, not just the most singular term, but the exact entropy. And so this was understood in this paper. And since then, there has been a very large body of works that tries to understand the Cardy limit and the large n limit and various properties of this kind of indices. And I think that the understanding of this subject has been greatly improved in, let's say, the last 3-4 years. So I just listed here some papers, but there's like a large body of works, but they are somehow all revolving around this circle of ideas.
Thank you. That was very useful. So any other questions? If not, then let's thank Luigi and also Irina for their great talks.
Thank you.
Let me stop the recording.